In this video, we'll only cover one section, that's G, solids of revolution. Now recall back where our journey of integration began. We were discussing finding the area underneath a curve by dividing that area into more and more and more rectangles. And as we made more and more and more rectangles, then the sum of their areas combined better and better approximated the area underneath the curve. And if we had essentially infinite rectangles, and if we took the limit of their areas as the number of rectangles approached infinity, then their areas approached the true area underneath the curve. And good news, integration is not bound by 2 dimensions. No, we can do this in 3 or higher dimensions as well. It's essentially the same process. We're going to take a volume now, slice it into infinitely thin pieces, and when we add up all of their individual volumes, we'll get the volume that we're interested in. So there's a few different types of volume problems. We're going to focus on solids of revolution, which is absolutely the number one big one for the IB and the AP. But at the end, I'll also touch on a few other different variations of volume problems that you might see. Certainly more popular in the AP program, but it's the IB, you never know. So the idea, as we see here, is that we're going to have some function, f of x, and it's going to rotate around the x-axis 360 degrees, 2 pi radians, all the way around to form a solid. All right, 2 things I want to point out. First of all, I've never seen a problem where it did not rotate all the way around exactly once. Second, I don't think it's the most important thing, but I think it's nice if you can visualize what this solid of revolution should look like. So take a moment, try to imagine this in your head. Some of you will find this easier than others. Hopefully you're imagining something like this.
I don't think you'll gain any sort of competitive advantage, but I just know it always made me feel more comfortable, at least when I was doing problems like this, if I could get a pretty good visualization going in my brain of, what the volume of revolution would look like.
I want to go through the big idea process here and connect it back to limits really quickly because this will inform us as to where the formula comes from, and it's not too hard to understand. So the basic idea is that we want to get this entire volume of revolution. And in order to get that, we're going to take very, very narrow slices of that volume and add them all together. And if we add up all those different slices of volume, then we'll get the whole volume. Well, let's look at each of those individual slices. They're almost perfect cylinders, right? Not quite, because these two curves probably aren't parallel to each other, but as we take narrower and narrower slices, they do become closer and closer to being perfect cylinders. And so we know that the volume of a cylinder is going to be pi r squared, because that's the area of the base, multiplied by the height. Well, what is the radius for each of these? Well, the radius is simply the height of the curve, which is given to us by the function. So instead of r, we think about f of x. And then the height of each of the cylinders is really just the horizontal distance from the beginning of the slice to the end of the slice, which, since we're making these slices narrower and narrower, that means we're taking the limit as h approaches 0. And then we're adding up all of these slices. And adding up infinitely many things is how we arrive at a definite integral. So this is the formula that we need to know. It's pi multiplied by our definite integral, not of the function, but of the function squared. And if you can't remember that, you always just have to think, what am I actually adding up? I'm adding up a bunch of essentially infinitely narrow cylinders. So really you're just adding up a whole bunch of circles areas. And then as we move those areas through this third dimension, we get a volume. And so circle's area is pi r squared. Also, the formulas are in the data booklet. They're on page 13. You're going to see this and this on that page. So they do tell you how to take the volume along the x-axis or along the y-axis. Now again, these are the formulas when we are rotating 2 pi. So when we're going all the way around our x or y axes. All right, simple example here. We've got function, we've got a domain, We're revolving at 2 pi around the x-axis. Okay, this question is telling us to do a definite integral from 0 to 5 of x to the 4th, and then multiply that by pi at the end. Easy. In this example, we want to rotate around the y-axis, which means we're not going to think about y equals ln of x. Instead, we're going to consider its inverse. So we're going to say x equals e to the y. And then we need to change our endpoints. So instead of 1, remember this is an x value, so we can say 1 equals e to the y. What should the y value be? Well, that's going to be 0. And then when e equals e to the y, that's going to be 1. So we've got a definite integral from 0 to 1 of e to the 2y, and then multiply that by pi. Next, you probably remember that we did area in between two functions, and so we're also going to do volume in between two functions. So we're going to rotate both of them around the x or y axis. So how would we find this? Well, look, basically we're just taking the volume generated when we take the top function and revolve that around the x-axis, and then we're subtracting away the space in the middle, which is exactly the volume we would get if we took the lower function and revolved it around the x-axis. So you could think of this as two integrals, one minus the other. You could do pi times, in this case, f of x squared minus the integral of pi times g of x squared, or usually we just put them together into one single integral, as we see over here, since they both have the exact same endpoints and they're both being multiplied by pi. Just be careful, it's not f of x times g of x all squared, it's f of x squared minus g of x squared. Or again, you could think of it as they have down here, the subscripts indicating this is the upper y value squared minus the lower y value squared. Just like we thought about with areas, top function minus bottom function, same idea here. And if we were to do something like this around the y-axis, it'll be the function on the right squared minus the function on the left squared. So just like with areas, we need to work out the point of intersection of the two functions. In this case, it's pretty obviously 1, 1, but if you didn't know that, you would just set these two equal to each other and then solve. And they've got to intersect someplace, because if they didn't, if you thought that maybe one function was above the other the entire time, then like, I don't know, what are the endpoints of your integration going to be? We don't have any. So they've got to intersect somewhere. So figure out where that is, and then just put everything else into your formula. It's easy from there. Okay, at this point we've seen everything that's in the IB syllabus. You might have a lengthy problem where part A asks you to find the points of intersection between two curves. Part B may ask you to find the area between them. Part C may ask you to find the volume when you revolve around the x-axis. Part D may ask you to find the volume when you revolve around the y-axis. And by the way, in the previous video, we saw that the area, when we integrate with respect to x or with respect to y, of course the area is going to be the same in both cases. However, we would not expect that to be true for volumes, right? I mean, depending upon how far away that area is from the x-axis or the y-axis, we should expect to get different volumes when we revolve around different axes. Anyway, what I want to finish the video with is just to look at a few other extensions of volume problems with a focus on AP problem types. And this isn't just in case you're taking the AP exam. Of course, the IB could ask questions like this if they scaffolded a question appropriately to try to lead you towards this new idea or understanding or whatever. Now, I was just randomly opening up old AP free response questions, and I found this one, which is nice. There's nothing special about this particular question, but it does illustrate two of the big points that I wanted to make. First, I want to look at, in part A, we're finding a volume of revolution where we're revolving neither around the x nor around the y-axis, but around some other horizontal or vertical line. So we've got a quartic function and the line y equals 4. We want to find the volume when we take this area rotated around not along the x-axis, which would be the line y equals 0, but about the line y equals -2. So a couple things we're going to need to work out. First of all, we need to figure out what are the actual endpoints there, which we would want to use a calculator for this, really, because we're solving a quartic equation. Doesn't really seem like the easiest thing here. Yeah, we're not doing that by hand. So whatever, you grab a calculator, you'll find out those two x values are 0 and 2.3. I don't think I should walk through how we can get that. I think we know how to do that. But now for the integral that we're going to work out, yeah, it's still going to be pi times some stuff. But we need to be careful because we're not revolving around this line. Instead, we're revolving around this line down here. The only thing that changes about this is, well, I mean, you could imagine shifting everything up 2 units, right? Because this is the line y equals -2. And if you do that, then, I mean, you're smart enough to figure this out. Instead of y equals 4 being the top function, if we shifted everything up 2 units, this would become 4 plus 2. This would become 6. And then the bottom function, instead of being that quartic function, which let's just call it f of x for short, what would that bottom function be? Well, again, it would be shifted up 2 units. So we would now have f of x plus 2. And that's exactly the integral that we're going to work out. The endpoints are going to be 0 and 2.3. We're multiplying by pi. Our first function becomes 4 plus 2 squared. Our second function is f of x plus 2 squared. You grab a calculator, you do all that, and you get one of these two answers. The AP is so cute, they don't even require you to round correctly. Let's change this thing around for a second now. What if we were revolving around the line y equals 5? So now that's going to be a line that's actually up here. What are our two functions going to be? Well, now instead of thinking about the top function minus the bottom function, the way we want to really conceive of this is we want to take the function that is farthest away from the axis and put that in here first. You know, most of the examples that you see in textbooks and websites of how to do these volume problems, they always have both of the curves be above the x-axis. So you're always thinking top minus bottom. But really you should be thinking outer minus inner, the outer radius minus the inner radius. So in this case, if this is our axis of rotation, what is the outer function? The outer function is going to be the distance from that horizontal line to this curve f of x. What is that distance now? Well, the distance from the x-axis to the line y equals 5 is 5, obviously. But then we are subtracting away this distance, and this distance literally is f of x. So here we're going to have 5 minus f of x, and then here in the second bracket it's going to be 5 minus this distance here, so 5 minus 4. So you see that with a little bit of thought, you should be able to work out what your inner and outer functions are going to be, regardless of whether the axis of rotation is above your two curves, below your two curves, below them, but in between them and the x-axis, whatever, you should be able to come up with it. And the good news is that the order that you put them in, it doesn't really matter, because if you get that wrong, you're going to get a negative answer, and then you just need to be smart enough to take the absolute value since you're finding a volume. So that's it for revolving around other horizontal and vertical axes. I mean, technically you could revolve this region around any line that you wanted to, but you would require some more high-powered mathematics to redefine what the two functions are. So we're definitely not going to get into that here. The second point that I wanted to hit with this question is about volumes that are actually not volumes of revolution, but volumes that still have us adding up a whole bunch of essentially area slices in order to accumulate an overall volume, and that's what we see here with part B. So in part B, our region R is the base of a solid with cross sections perpendicular to the x-axis, each being an isosceles right triangle. Now, the problem here is that I absolutely cannot draw this, and I don't have computer software to really generate what we're looking at here. So I'm going to try to coach you through what you want to see. If I'm not successful, I'll show you some other pictures at the end of other problems so you can kind of imagine this. So for this problem, we've got perpendicular to the x-axis, so running parallel to the y-axis, we have the bases of these isosceles right triangles. So I want you to imagine each slice is one leg of an isosceles right triangle. The other leg is going to actually be popping out of your computer screen towards your face, and those other legs will be coming off of this green line. So the leg that we see coming at your face from right here is going to be the same length as this one because it's isosceles. The length that we see from right here is going to be the longest one, and so on. So we've got some weird sort of shape happening here. It's hard to visualize, but what are we going to do if we want to find the volume of this whole shape? Well, we're going to integrate from here to here, and we're going to add up all of those isosceles right triangles. We've already worked out what these two values were. They were 0 and 2.3. So from there, we just need to integrate, and we need to integrate the area of an isosceles right triangle. What is the area of an isosceles right triangle? Well, it's going to be 1/2 the base times the height, but the base and the height are the same thing, so we just need to figure out what that base length should be. And that base length is going to be this length, which is not f of x, but it is, since this is y equals 4, this length is 4 minus f of x. And so you'll get something like this, and that's all there really is to it. You just have to figure out, again, what is the shape that we're dealing with. In this case, it was an isosceles right triangle. What is the area of that shape? Okay, well, it's 1/2 times the base squared, and then figure out what the base is in terms of the functions that you're dealing with. Now, I kind of think of this as being kind of like finding the volume of a prism, only I'm obviously breaking a few of the rules here. Like with a prism, I would have two parallel bases which would be congruent. So in this case, those are going to be these two isosceles right triangles. And I would, to find the volume, I would take the area of one of those and then multiply that by the height. In this case, my height is really the distance from 0 to 2.3. Now, my two bases are not congruent necessarily in a problem like this, and certainly all of the cross-sectional slices in between them are not going to be congruent to the two bases, but they're all similar shapes that have the exact same area formula, and so that's kind of what goes into this idea up here. And again, that really is what integration is about. We're adding up infinitely many tiny, tiny pieces to get a whole. Now, for those of you looking for visuals, I don't know. I actually had some difficulty finding some good pictures of this. This one's from one of my other textbooks. So here we have the cross sections are all semicircles. Yeah, you could think of it as taking this part of the curve and then revolving it 1π around the y-axis, but you can also just think of it as having this, looks like it was a sideways parabola here, and then having semicircular cross sections. Down here we have the same curve 4 times y equals x squared. And we have different types of cross sections producing different three-dimensional shapes. So it looks like semicircles. I don't know, this looks like a rectangle where there was perhaps some sort of a relationship between the height of the curve and then the three-dimensional height of the rectangle. Maybe these are squares. These look like they're right triangles of some sort. But really, it's the same idea for all of these. You've got two endpoints, so you're going to integrate, from A to B, and then you've got some shape popping out of the page at you that you should know how to find the area of. And you're just going to need to figure out what that area is with relation to the function or functions that you're looking at, put it into your integral, and you're good to go. So far in this video, we've been discussing the disk and washer methods of finding volumes of revolution. I do want to point out there is a whole other method out there. It's called cylindrical shells, You'll find it in most calculus textbooks, but it's not required on the AP, nor is it required on the IB. If you want to go out and learn it, that's great. You might find that it might make certain problems easier for you to think about them in terms of shells instead of in terms of disks and washers, but in the interest of time, I'm not going to get into it here. Totally optional. Go out there and learn some more math if you're interested. The final thing that I want to say is that now that you know some of this basic integral calculus, you can now have the joy, the excitement of proving all sorts of area and volume formulas that you've been taking for granted since you were a little kid. I'll show just a few of them here. I'm not going to go through the full integrals, but I'll sketch out the beginning of it so you can see how it works out. So say I wanted to find the volume of a sphere. All right, so the answer to that, hopefully we know, is 4/3 pi r cubed. We can work that out using integration. So we have a generic sphere of radius r, and if we take the semicircle here, of which this is the equation, the idea is we're going to revolve that semicircle, right, 2 pi around the x-axis, and we'll get a whole sphere, and we want to work out its volume. So what do we need to do? Well, we've got to calculate an integral from, well, my left endpoint is negative r, my right endpoint is positive r. That's volume of revolutions. Let's not forget the pi. And now I'm going to put in r squared minus x squared dx, since I'm squaring that function. And I'm just going to evaluate that definite integral. Keeping in mind that r is a constant, this will get you, and you can check this yourself, this will get you 4/3 pi r cubed. But there's an entirely different way we can do it using surface areas. So if we take the surface area of a, let's say, a really tiny sphere, actually we're going to start with the surface area of an infinitely small sphere right at the origin. And we're going to take that sphere and we're just going to start to inflate it, blow it up until we get to the size that we're looking for. If we add up all of those individual surface areas, we should get the total volume. So here we're thinking in the same way that we were with the cross-sectional areas earlier. So we can do it that way. Actually, this integral ends up looking a little bit simpler. Well, we need to know what the formula for the surface area of a sphere is. So that's going to be 4 pi r squared. So I'm going to take my 4 pi outside of my integral. Now here, what am I integrating from? So my very smallest sphere is going to have a radius of 0. So I'm going to put that there. And then my biggest sphere is going to have a radius of r. And all I'm going to put in here is x squared dx, where x is the radius of the sphere at any point in time. And those are both going to get you the same answer, aside from the fact that I chose a lowercase r here and a capital R there. That was for no important reason. So I don't know, have fun with this. See what other area and volume formulas you can derive using these techniques, either revolving or adding things together. Like you can get the area of a circle, for example, by integrating circumferences of smaller circles to bigger ones in the same way that this second example just worked out. So go crazy, have some fun with it. See what formulas you can derive by applying your newfound knowledge of calculus to. Maybe you'll enjoy it as much as I do. Probably not, though.